Our topic today is wave data analysis. In this topic, we're going to look at how we analyze raw data collected, and it's different from our previous discussion about small amplitude wave theory, whereby we already know the properties of the wave such as wave height and wave period. Here, wave data analysis is taking the raw measured data in order to analyze the wave period, wave data, and other properties. If we use the same method to analyze wave period, then we can also get the significant wave period. We can also get the T10, but usually the spread of the wave period is less compared to the wave height. So in most record or most observation, the significant wave period are usually quite close to the top 10% the wave period, and they are usually about 1.2 of the average wave period. So this is the rule of thumb, right? Both the wave height and the wave period, as mentioned, are analyzed in the same way. We have looked at this histogram just now in our example. So if we have a histogram of the wave height like this, whereby vertical axis is the numbers and the horizontal axis is the wave height, we can convert this data into a probability plot, whereby the vertical axis is the probability density and the horizontal axis is the ratio of the wave height compared to the average wave height. And this is what we are going to do next. We are going to look at the characteristic of this probability distribution of wave height, which is commonly fitted using a Rayleigh distribution. If we plot the wind wave statistic in terms of the probability distribution as a function of the wave height, as mentioned, we typically get a distribution with a shape like this. Here, the probability function of the wave height is given by this expression, whereby h RMS here, and here is the root mean square height, which is defined mathematically in this equation. Now, if we use the probability distribution and perform integration from 0 all the way to the maximum wave height, then we get the cumulative probability distribution below the curve. And we write that as capital letter P in bracket H for the wave height. So this refers to all the waves that possibly happens. And so if we define a particular wave height H, let's say this value, then 1 minus the cumulative probability distribution will be this area here, and that area represents the percentage of the wave that exceed this particular wave height. So essentially, the cumulative probability distribution, which covers the entire curve, should equals to 1, and 1 minus the cumulative probability distribution up to a point give us the percentage of the wave that is more than that particular wave height. This slide here shows the typical characteristic of a Rayleigh distribution. Of course, if we have long enough observation, in most cases we are going to find that the wave observation fulfills the Rayleigh distribution. However, if our observation is short, then our analysis may not follow the Rayleigh distribution exactly. Here, the correlation given is for long wave observations, whereby for long enough observations, we expect that the wave to follow this kind of behavior, where the average wave height or mean wave height is typically 0.886 of the HRMS. The significant wave height, the H1/3, generally is square root 2 times HRMS, which is basically 1.416 times HRMS. And the maximum wave height usually is given by this expression, where n is the number of waves observed in the data. The characteristic can also be summarized in a table like this. Here we have n, which is the percentage. Here we have hn over h1/3. So h of 1% of the wave typically is 1.68 of h1/3. H of the highest 10% of the wave typically is 1.28. h1/3 is over h1/3 is equals to 1. h50, that means h average h value of the 50% of the wave is usually about 0.89 of h1/3, and h100 basically is the average. So the average width height usually is about only 0.63 of h1/3. I repeat one more time. The highest 1% of the wave usually will be about 1.68 of the h1/3. The highest 10% of the wave usually is about 1.28 of the h1/3, etc. So likewise, we can say that the highest 1% of the wave is usually about 2.68 of the h average. The highest 1/3 of the wave, which means the h1/3, is usually about 1.6 of h average, and so on. Now from the previous slide, we know that the Rayleigh distribution shows h average is equals to 0.886 of HRMS, and h1/3 is equals to 1.6 of h average. If we combine these two, you notice that h1/3 is equals to 1.6 times h average, wherever h average is actually this, so we put it inside here. So if we calculate, we get h1/3 is equals to 1.416 of HRMS, and you can find this in the previous slide as well. So basically they are all consistent. Now let's take the equation for the cumulative probability distribution from the earlier slide, and let's write out the equation, and the h inside the bracket is the value of weight height that we want to analyze. Let's say we want to analyze the h1/3. So we substitute h1/3 into here, Alright, so now we are going to calculate the value of the cumulative probability distribution of h1/3. So the cumulative probability distribution of h1/3 is given by this expression, and h1/3 over HRMS is basically 1.416, which is from here. And so we found that the Answer here is 0.865. The cumulative probability distribution of H1/3 is 0.865. It means that in the entire curve in the Rayleigh distribution, from 0 up to H1/3, the cumulative probability distribution is 86.5%. That means that 86.5% of the waves is equal or less than the H1/3. And if that is the case, that means that the balance, which is 13.5% of the waves, is expected to be larger than H1/3. Now, if you understand this concept, then you understand what it means by this cumulative probability distribution. But meanwhile, I also want to highlight about these two values here. We have H1/3 and we have this 13.5%. Remember that if we have a complete record, we get H1/3 by taking the highest 1/3 of the waves and average it out. Now, if we take the highest 1/3 of the wave and average it out, so the average value should be somewhere here, in the middle of this 1/3. So if the waves fulfill the Rayleigh distribution, then the H1/3 should be located somewhere here, so that 86.5% of the wave is equal or less than it, and 13.5% of the wave is more than it. This is a chart that summarizes the characteristic of Rayleigh distribution for different wave height. On the horizontal axis here, we have H over HRMS, and on the vertical axis here, we have the values for P given by this curve and N given by this curve, where P is the probability of exceedance and N is the percentage. So basically what we have shown previously in terms of the equation for Rayleigh distribution is represented here in graphical form in the chart, and we are going to look at how it can be applied next. Let's look at this example. A wave record taken during a storm is analyzed by the zero upcrossing method and contains 205 waves. The average wave height in a record is 1.72 meter. Estimate HS, that means the significant wave height. H5, that would means the highest 5%, the average of the highest 5% wave, and the number of waves in the record that would exceed 2.5 meter. Okay, so we're going to start with the first one. We want to estimate the significant wave height. Now, assuming that the wave fulfills the Rayleigh distribution, then we know that average wave height is equals to 0.886 of HRMS. So if we rearrange this equation, we are able to calculate the HRMS, which is 1.94 meter. And also, if the wave fulfills the Rayleigh distribution, then H1/3 must be equals to 1.416 of HRMS. So that will allow us to calculate the significant wave height, which is 2.75 meter. Now, if we stop here, you notice that we're talking about a short-term wave record with only 205 waves. We didn't have the actual raw data, but we do know that the overall average is 1.72 meter. We assume that the wave fulfill the Rayleigh distribution, and based on that assumption alone, we are able to apply all these equations, and that allows us to calculate the significant wave height without having to actually sort out the top 1/3 of the wave height and average them out. So that is what we get if the Rayleigh distribution is assumed. Now if we look at the chart, the same solution that we have just derived are actually inside here. Just now we were trying to work out the significant wave height, which is the h1/3. 1/3 is about 0.33. So for n equals to 0.33, which is somewhere here, alright, somewhere here, this line. Take note that for this vertical axis, the smaller number is on the top. We have 0.01 here, with 0.1 here, with 0.5 here, 0.33 is somewhere here. So for n equals to 0.33, if we will go to the curve n and read down, you notice that we have about 1.42. So h over h RMS is 1.42, which basically is this relationship. And for h over h RMS equals to 1.42, if we go all the way up to this curve, which is the probability distribution, and if we read across, we find that the value is 0.135. So that is the same as what we saw from the previous example, which says that for h1/3, 13.5% of the waves are larger than h1/3. Okay, so now we're going to move on to estimate the h5. So if we're going to estimate the h5, let's say we're going to use this chart right now. So our interest is h5. So we will find out h5 from the chart. h5 represents the top 5%, which means 0.05. 0.1 is 10%, 0.5 is 50%, so 5% is this 0.05. So for n equals to 0.05, the h over h RMS is approximately 1.98. And which means that h5 is 1.98 times h RMS, so h5 is 3.84 meter. So again, we are able to obtain the h5 based on the Rayleigh distribution here without actually sorting and averaging out the top 5% of the wave record. What we did is we assumed that the wave record fulfills the Rayleigh distribution. Next, we want to find the number of waves in the record that would exceed 2.5 meter height. So we are interested in the wave height h being equals to 2.5 or larger. So we set h equals to 2.5, we divide by the h RMS is 1.94, we get h over h RMS of 1.29. This is the axis for h over h RMS. 1.29 is located somewhere here. And so from this, if we read to the curve P, we obtain 0.19 approximately, which means 19% of the waves are expected to be larger than this wave height 2.5. And since we have 205 waves here, 19% of 205 waves is 39 waves. So we expect that out of our wave record, there are about 39 waves with wave height more than 2.5. We'll discuss about the time domain analysis, and now we're going to move on to the frequency domain analysis. Now, as we've mentioned previously, the wave observations record is made up of a superposition of large number of waves with different wave height and also different wave period. So essentially, energy spectrum means the energy distribution over frequency. That means how much energy there is for a particular frequency or for a particular wave period. Now, in order to do that, we will have to perform decomposition so that we are able to break down the original wave into their individual component, whereby each component have a different frequency or a different wave period. As you can see here, this will be a wave with a larger frequency because it has a shorter wave period. This will be a wave with a lower frequency with a longer wave period, right? So a mathematical decomposition will allow us to break down the original wave data into their components. And what we're going to do next is that we are going to analyze the total energy in each of the frequency. So this method is called spectral analysis. It's basically a technique of decomposing a complex physical phenomena into individual components with respect to their frequency.